This presentation will discuss the ideal gas law, also known to chemists as PIV-nRT. But before we start there, we're going to review an example of a traditional gas law problem. This warm-up example states, the pressure in a car tire is 198 kilopascals at 27 degrees Celsius. After a long drive, the pressure is 225 kilopascals. What is the temperature of the air in the tire? Assume that the volume is constant. Previously in section 10.3, we looked at three main gas laws, Boyle's, Charles, and Gay-Lussac, and they were all equations that involved two variables, including either pressure, volume, or temperature. This is a classic example. If you take a look at the information provided in this problem, it says the pressure in the car tire is 198 kilopascals. So we know pressure 1 is 198. We also know the initial temperature is 27 degrees Celsius. Now I would discourage you from actually writing the problem in Celsius, or the information in Celsius, because then you might be tempted to use it in the problem. And if you recall, in order to change Celsius to Kelvin, we need to add 273. So that means our initial temperature is 300 Kelvin. After you drive for a while, the pressure in your tires is typically higher. And in this case, P2 is 225 kilopascals. And the question is, what is the temperature of the air in the tire? So T2 is what we are looking for. And it is helpful to identify the variables that we have so it can kind of point us in the correct direction of which equation to use. So of the three equations we worked with in section 10.3, this one is pressure and temperature, which is the Gay-Lussac equation. So P1 over T1 equals P2 over T2. And if we plug in those values we've been given, 198 kilopascals over 300 Kelvin equals 225 kilopascals over T2, or X. If you cross multiply and divide, you will find the new temperature is 341 Kelvin. And you might wonder why the temperature of the gas in your tires is warmer. And if you think about the friction between the tires and the road, that tire itself is going to warm up, which in turn will warm up the gas inside, which means that there will be more energy, the gas particles will move with more energy and collide with more force against the surface of the tire, and that's why your pressure goes up. So that's a quick example of the previous section. One of the things you'll notice about the previous section is that three variables included were pressure, temperature, and volume, and there was really nothing about amount of gas. And as a lead into section 10.4, we need to talk about the Avogadro hypothesis and law. And the Avogadro hypothesis states that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Avogadro also developed his law, which is known as the volume of a gas at a given temperature is directly proportional to the number of moles of gas. And what we find here is this is the first place we really introduce anything about number of gas particles or amount of gas. Previously, we've just been working with pressure, temperature, and volume. And this is important because our most widely used gas law of all the gas laws equations in chemistry is the ideal gas law, and this is our focus in section 10.4. The ideal gas law equation is PV equals nRT, commonly referred to as PIV-nRT by chemists. And a couple of things to observe. First of all, this is a very different looking equation than any of the equations from section 10.3, because all of those equations were things like PV equals PV, or P over T equals P over T, and there were two of each of those variables, two pressures, or two volumes, or two temperatures. If you take a look at this equation, there is only one of each variable, one pressure, one volume, one temperature, and in addition we have two new variables as well. P in this case, as it has before, stands for pressure, and it can be measured either in atmospheres, millimeters of mercury, or kilopascals. V is volume, and an important thing to make sure you note is that it absolutely has to be in liters. It cannot be in cubic centimeters, it cannot be in milliliters, it absolutely must be in liters in order for the units to work out properly. N is a new variable for us, and it stands for moles of gas. And one important thing to understand is sometimes you'll be solving for moles of gas, but sometimes this N can be used to find grams. So if you are asked to find the amount of mass of gas in a balloon or in a vessel or something like that, you'll find that mass is not part of PivNRT, but moles of gas is. And so if you are asked to find anything with mass, make sure you find N first, and then you can convert it to grams. R is the ideal gas law constant, and there are 3 values of that, which we will discuss in just a moment. And T, again, is temperature, and it must be in Kelvin. So if you are given the temperature in Celsius, it will have to be converted to Kelvin by adding 273. Now there are 3 different values of R. The numerical values are 0.0821, 62.4, and 8.314. And as you look at the 3 values for R, obviously the numbers are different, but aside from that, the labels, if you take a look at those, all of them have liters in the numerator, and all of them have moles Kelvin in the denominator. And so really the only thing that changes is the pressure unit. And so 0.0821 has atmospheres, 62.4 has millimeters of mercury, and 8.314 has kilopascals. And so depending on which pressure unit they give you, that will determine which value of R you will want to use. One of the things that's often discussed when we bring up PivNRT is something referred to in chemistry as STP. STP is an acronym that stands for Standard, Temperature, and Pressure. The conditions at standard temperature and pressure are 0 Celsius, or 273 Kelvin, and 1 atmosphere. And a lot of times we refer to those conditions so we can compare different gases at a common set of conditions and see how they vary. We also in chemistry define something known as the molar volume of an ideal gas. And that sounds a little bit confusing at first, but if you think about molar volume, that implies the volume of 1 mole of gas. And since it's at ideal conditions, we know that it has to be at 0 Celsius and 1 atm. Now the value for the molar volume of an ideal gas is 22.4 liters. And that's telling us that 1 mole of any gas, no matter if it's hydrogen, carbon dioxide, methane, 1 mole of any gas at 0 Celsius and 1 atm should occupy a volume or take up the amount of space equal to 22.4 liters. And you might say, well, where does this number come from? If we take a look at PivNRT, PV equals nRT. First of all, we know that molar volume is the volume of 1 mole. So we know that N has to be 1 mole. We also know that if we're at STP, the temperature has to be 0 Celsius, or in other words, 273 Kelvin. And we also know that the pressure needs to be 1 atm. If we use PivNRT and we're solving for the molar volume of an ideal gas, which would be V in this equation, if I rearrange, V would equal nRT divided by P. So if I plug in all those numbers, N would be 1. R, now remember we have 3 values of R, 0.0821, 62.4, and 8.314. And we want to use the one that includes atmospheres, since our pressure is in atmospheres. So we're going to use 0.0821. And it is important to include these labels: liter atmospheres over moles Kelvin. And then our temperature is 273 Kelvin. And our pressure is 1 atm. Now taking a look at how these labels cross out, and you might have wondered, like, why in the world does R have such crazy looking labels, liter atmospheres over moles Kelvin? Well, if you take a look at how things cross out here, moles will cross out, Kelvin will be eliminated, as well as atmospheres, which leaves liters in this case. So if you go ahead and crunch this out on your calculator, we should get an answer of 22.4 liters. And so no matter what gas we have, if we have 1 mole of it and it is at the conditions of 1 atmosphere and 0 Celsius, it will have a volume of 22.4 liters. We're going to take a look at some examples using the ideal gas law equation, or PIV-nRT. And this first example, 1.05 moles of carbon dioxide gas is placed in a 2,500 cubic centimeter container at 25 Celsius. What is the pressure measured in atmospheres inside the container? So if we take a minute to label what we've been given in this problem, it says 1.05 moles of CO2 gas. So I know N is 1.05 moles. We know the container is 2,500 cubic centimeters. Now we have to be very careful. When we talked about PIV-nRT, we said that the volume has to be in liters in order for our units to work out properly. A cubic centimeter is the same thing as a milliliter. So when you look at 2,500 cubic centimeters, really I right away think of 2,500 milliliters. That's a little easier to visualize to do your conversion. If you move your decimal 3 places to the left or divide by 1,000, you would get 2.5 liters. So that's our given volume. The temperature is 25 Celsius, which in Kelvin would be 298. Oops. Not cooperating here. I'll write over it. 298 Kelvin. And what is the pressure measured in atmospheres inside the container? So we start with our PIV-nRT equation, PV equals nRT. And I personally like to rearrange the equation for whatever variable I am solving for. So if we're solving for pressure, if I want to get that by itself, it would be nRT divided by V. And then we plug in our information, 1.05 moles. Again, we have 3 values of R, but we need the one with atmospheres because it asks us to find pressure in atmospheres. So 0.0821 liter atmospheres over moles Kelvin. Temperature 298, and the volume 2.5 liters. And looking at that setup in terms of labels, moles will cross out, Kelvin will cross out, liters will cross out, which will give us a pressure in atmospheres. If you go ahead and solve for that, you should get 10.3 atmospheres. And make sure as you are working, you do take time to check these calculations to make sure you're getting the right answer. Example 2. How many grams of N2 are contained in a flask with a volume of 250 milliliters at a pressure of 3 atmospheres and a temperature of 300 Kelvin? Now, one thing I want you to notice right away about this problem is that it asks us to find grams. And there isn't a mass variable in PIV-nRT, so what our plan is going to be is we're going to have to find N moles first and then convert that to grams when we're done. So if we take a look at our equation here, PV equals nRT, we know we want to find grams, so we have to first find moles. So if we rearrange and solve for N would be PV over RT. If we plug in our information, the pressure is 3 atmospheres. The volume, 250 milliliters. We have to divide that by 1,000 or move your decimal 3 places to the left to convert it to liters. So that would be 0.250 liters. The R value, I need to use the R value with atmospheres, so 0.0821 liter atmospheres over moles Kelvin. and the temperature will be 300 Kelvin. Now a lot of students will get to this point, they'll crunch out their answer, and they will get 0.03045, and they think they're done. But if you go ahead and cross out your labels, atmospheres are gone, liters are gone, Kelvin is gone, that will leave moles. And the question asked for grams of nitrogen, not moles of nitrogen. So there is that added step of having to change moles of nitrogen into grams. So if you consult your periodic table and obtain the mass for N2, 28.0134 grams, keep in mind it is diatomic, you should get an answer of 0.853 grams of N2. Ooh, that's an ugly looking circle. Much better. Example 3. A balloon contains 0.873 grams of hydrogen. How big will the balloon be at 22 degrees Celsius and 742 millimeters of mercury? Now I'd encourage you to pause the video and try this one on your own first, and then go ahead and continue playing and see if you've come up with the correct answer. One thing you'll notice on this one is we are provided with grams. Those grams have to be changed into moles. A common mistake is for students to plug 0.873 in for N, but N is moles, not grams. So one of the first things we would want to do is take 0.873 grams of H2 and change it to moles. And using your periodic table again, 2.0158 grams is the molar mass of hydrogen. And I'm not going to round to sig figs right here. I'm going to round once at the end. I would get 0.43308 moles of hydrogen. And when it says how big will the balloon be, we are talking about volume or size of the balloon. So if we look at PIVNERT, PV equals nRT, we know we'll be solving for volume. So rearranging, getting V by itself, I would have nRT over P. And making our substitutions with our values, 0.43308 moles. R, now this time we have to use the R that includes millimeters of mercury for the pressure, and that value is 62.4 liters times millimeters of mercury over moles Kelvin. Our temperature, now 22 Celsius, remember you have to add 273 to convert it to Kelvin, so we have 295 Kelvin. And then our pressure is 742 millimeters of mercury. And so looking at our labels, moles are gone, Kelvin is gone, millimeters of mercury are gone, leaving liters, which is an appropriate label for volume. For this problem, we should come up with 10.7 liters. So those are some good examples with PIVNERT and grams and those types of things. The other section that we're working on today, it's not called this in the textbook, but I don't know, it was like further applications, blah, blah, blah. So I just thought more fun with PIVNERT sounded better than whatever they had. So the other section is going to look at a couple other forms of PIVNERT with some substitutions. And the two main applications we will include, instead of just pressure, volume, temperature of gases and amount, are gas densities and also molar masses. And one thing to keep in mind as you are looking at density of gases, normally densities are, the formula for density is mass over volume. And typically for most solids and liquids, that would mean we would use grams per milliliter or grams per cubic centimeter. But gases have such low densities compared to solids and liquids that instead we want to use grams per liter. Now, one of the things we have to kind of watch as we're looking at these labels is liters is the unit for volume when we're working with PivNert. So sometimes instead of grams per liter, we could say grams per volume. Molar mass, which is abbreviated M, and it's more of kind of like a script M or a kind of a cursive M. The way that fits into this equation is, if you think about it, we use it when we're trying to determine moles. So if you want to find the moles of something, N, you would take the number of grams of that substance divided by molar mass. So if we put in grams over molar mass, then we can work, put that in for N, we can also work molar mass into these equations. So rearranging these different, including these different variables and rearranging, we can come up with a couple different forms for PivNert. And let me show you what I mean. If we start with just PivNert, and we substitute the idea that we find moles by taking grams over molar mass, I could get PV equals grams over molar mass RT. And then if we rearrange a little bit, divide both sides by V and multiply both sides by molar mass, which essentially means I'm going to end up switching these two variables, I would get P, pressure times molar mass, equals grams over volume, RT. We also said that density is grams per liter for gases or grams over volume, so that would mean that I could make another substitution, pressure times molar mass equals density times RT. From there, we get two very useful equations, and I would suggest you highlight these or put these in a box in your notes because they are very handy to use. And one of them is this same information rearranged as density, or solved, for density. So if I want to get the D by itself, it would be pressure times molar mass over RT. That's one of the main applications of PivNert. The other one would be to have it solved for molar mass. And if you isolate that in the equation, essentially you would just have to divide by pressure. So it'd be D density times RT over pressure. And we'll see one example with these equations. Oh, but before we do, speaking of density of gases, there's a couple cool video clips out there. Oftentimes we talk about, helium balloons and how if, a poor kid at a fair, they get a cool, fun helium balloon and they tie it around their wrist. And then the kid starts fiddling with it and they either let it go or it comes off their wrist and then bye-bye balloon and they're sad and all of that. And that's because helium, as a gas, its density is less than air, so it tends to rise. But there are also some situations where if you have a density of a balloon that's, or a gas, that's higher than air, then you can, it'll actually sink. The other clips we're going to see here involve breathing in helium and then speaking. I'm sure you've seen that many times and probably done it yourself. But you know that it does affect the pitch of your voice. And what happens is when you speak, your vocal cords vibrate. And they vibrate at a certain rate in the air that you are breathing. If you breathe in helium, which is less dense, the particles can actually make vibrations. The bright vibrations will happen more closer together, which will affect the pitch, and your voice will sound higher. However, if you breathe in something like sulfur hexafluoride, which I should say you should not go and do because it'll actually sit in your lungs and it's hard to get out of your lungs. There have been people that have suffocated because they breathed in sulfur hexafluoride and then they couldn't get it out of their lungs. But it will have the opposite effect. So rather than breathing in helium and making it like it will make your voice seem higher pitched, sulfur hexafluoride will make you sound like Darth Vader. So we'll watch a couple clips of those as well.
Alright, so this tank over here, it even sounds different when we fill it up. So here, listen to this. It sounds different. All right, so same thing you're going to do, but here's what I want you to do. I want you to all your air goes out, and then breathe in, and then I want you to do the intro to the podcast. Ready? Just tell our listeners at home something of importance. Ready? Here we go. He's bringing in the air. Some hexafluoride right into his lungs. See, now you can do that with some sort of. You're really doing that. You're not. There's no tricks behind the scenes or audio.
Post-production.
Is that it's still in your lungs, isn't it?
It's still in my lungs, but it's still young.
Yeah. Okay, now breathe in. You have to push it back out again. You're going to have to do that a couple times because that heavy gas is staying in. Get one more. There it is.
Hello, y'all.
You're back in this.
Now in this part of the video, the cool thing is sulfur hexafluoride is more dense than air, so you can actually put something in a container of SF6 and it'll float on top of the SF6 and it'll look like it's just levitating in midair. All right, on to the next one.
I'll be back.
Hopefully we are still recording here. And let's take a look at the last one. All right.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
Well, simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that, and my voice gets really low, although somehow I'm still funny. It's scientific!
All right, last 2 examples. The mean molar mass of the atmosphere at the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. Their surface temperature is 95 Kelvin and the pressure is 1.6 atmospheres. Assuming ideal behavior, calculate the density of Titan's atmosphere. So in this one, we're going to use the second example or the additional examples or applications of PivNRT. So density equals pressure times molar mass over RT. And if we plug those in, we would get 1.6 atmospheres times 28.6 grams per mole. That's the molar mass of the atmosphere there. And for R, we want to use the one with atmospheres, so 0.0821 liter atmospheres over moles Kelvin. And temperature is 95 Kelvin. And so atmospheres would cross out. Kelvin crosses out, moles cross out, and we get grams per liter, which is appropriate unit for density. And if you go through that calculation, we should get 5.9 grams per liter. And our last example, example 5, says the safety airbags in automobiles are inflated by nitrogen gas generated by the rapid decomposition of sodium azide. 2NaN3 yields 2Na plus 3N2. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres at a temperature of 26 Celsius, how many grams of NaN3 must be decomposed? So what we want to be careful of on this one is we want to use PivNRT, but we also are going to need to use stoichiometry. And so if you read the problem, you have a volume of 36 liters and a pressure of 1.15 atmospheres and a temperature of 26. All that information is about nitrogen. So our plan of attack is that we are going to start with PivNRT, but when we solve for N, it will be for moles of nitrogen gas. And then once, oh, why did that disappear? Once we have N, then we will be able to use stoichiometry to get, okay, that's very weird. We'll try it again. Hopefully it doesn't disappear again. Let me pause for a second. So PV equals nRT. If we rearrange, N would be PV over RT. So if we plug in the pressure, 1.15 atmospheres, the volume of the airbag is 36 liters. We need to use the R value, which has atmospheres in it, so 0.0821 liter atmospheres over moles Kelvin. The temperature would be 299 Kelvin, that's 26 plus 273. And if you solve that, you should get 1.6865 moles. Now be very careful. Again, that's moles of nitrogen. And so many students will take that number and go right to grams. However, we don't want grams of nitrogen, we want grams of NaN3. So we do need to use stoichiometry to finish this problem up. So 1.6865 moles of N2. And from the balanced equation here, we have 3 moles of N2. So I'm going to put that on the bottom so that moles of N2 will cancel out. And that's for every 2 moles of NaN3. And then our last step is to convert to grams. So 1 mole of NaN3, 65.00987 grams. And if we go ahead and crunch those numbers out, we would get 73 grams of NaN3. And that brings today's notes to an end. Hope that helps. Have a great day. Please email me if you have questions.